In the 1600s, René Descartes developed a very interesting way to talk about bodies in motion. He called it quality of motion, and it was the object's mass times the object's velocity. That quantity has changed names over time. At one point, it was renamed progress, and then it was renamed a third time as momentum, and that's what we know it as today. Now, in your lab that you did, we learned that momentum, which is represented by a lowercase letter p, is equal to the mass of an object times the velocity of that object. So let's do a quick calculation to practice. Let's determine the momentum of a 1,000 kilogram car moving northwards at 20 meters per second. So we know that momentum is mass times velocity, so all we need to do is take that 1,000 kilograms of mass, multiply it by that 20 meters per second velocity, and we end up getting that the momentum is 20,000 kilogram meters per second. Now, this is a vector. Momentum is. So that means that the positives and negatives are again going to become important because those positives and negatives represent direction. For us, we could say the positive direction is northward, so this positive 20,000 kilogram meters per second shows us that it is also northward. Now, very similar to our last unit on energy, momentum will be conserved, just like how energy was conserved. And in the 1650s, a Dutch mathematician named Christian Huygens began investigating those collisions, and he noticed that when a moving body struck an equal mass body which was at rest, the moving body would stop and the stationary would move at the same speed as the moving body. So he ran many experiments, some of which were the same as what you did in the lab, and he became the first person to write a statement of conservation of momentum. So one way we can think of conservation of momentum is that if we have one object of momentum m1v1 and it collides with a second object m2v2, then whatever momentum those two bodies have at the beginning must be the same as the momentum that those two bodies have after. Before is going to refer to before the collision happens, after refers to after the collision happens. And momentum is always going to be conserved in any collision. Another quality of motion, though, that relates to mass and velocity is kinetic energy. And kinetic energy is not always conserved. So we can categorize collisions into two different categories based on whether or not that kinetic energy is conserved. The first one, we call it an elastic collision. And for an elastic collision, momentum is conserved. And kinetic energy is conserved. Okay, so that statement of conservation of momentum that we made above is going to be true. And because kinetic energy is conserved, we can create another statement. We could say that the kinetic energy of object 1 and the kinetic energy of object 2 at the beginning has to be equal to the kinetic energy of object 1 plus the kinetic energy of object 2 at the end. So again, that's just giving us a conservation statement. This time it's with kinetic energy. The other category is an inelastic collision. So for an inelastic collision, again, it's a collision, so momentum is conserved. But for an inelastic collision, kinetic energy is not going to be conserved. So that little conservation of kinetic energy statement that we wrote directly above is not going to apply if we have an inelastic collision. So how are you going to know whether or not your collision is elastic or inelastic? Well, there's a couple of things that we can remember. For elastic collisions, we're talking about things like billiard balls. So if you're playing pool, those balls on the pool table, whenever they hit each other, we would consider that to be an elastic collision. Same thing with bowling. When the bowling ball hits the pins, we would expect that both the kinetic energy and momentum would be conserved in that collision. And the reason why is just a handy thing to think about is if things hit and bounce off of each other, it's probably going to be an elastic collision. But if things hit and stick, then it's probably going to be some kind of inelastic collision because the energy some of the energy has to go into making these things stick together, and that's why kinetic energy would not be conserved. Really, anything that's going to cause us to dissipate energy, that is going to be an inelastic collision. So something like car crashes, that would be an inelastic collision because some of our energy is dissipated. But overall, the thing I really want you to get out of this, the thing I really want you to stick with is regardless of whether it's an elastic or inelastic collision, no matter what, momentum is going to be conserved because momentum is always conserved in a collision, okay, no matter what. That's a common mistake of first-year physics students is that they think that inelastic collisions do not conserve momentum. No, momentum is still totally conserved in an inelastic collision. The thing that is not conserved is kinetic energy. Okay, so let's do 2 practice problems with this concept of conservation of momentum. A 5-kilogram ball moving at 8 meters per second strikes a stationary 85-kilogram man in the chest, after which the ball bounces at 2 meters per second. If the man, who is wearing high-quality rollerblades, was originally at rest, what is his final velocity? Okay, so there's a lot of information here. Let's try to write it all down in a knowns table. So we've got a 5-kilogram ball, and it is initially moving at 8 meters per second. We've got an 85-kilogram man. And then our ball hits him and bounces back at 2 meters per second. So that's, again, giving me information about V1. But it's now a final velocity because it's after the collision, and I would put that that is negative 2 meters per second since I'm moving now in the opposite direction. And these are vectors, so those positives and negatives are important. The man was initially at rest, so we will say that his VI is 0 meters per second, and we want to find out what is the final velocity of that man. So if we take our conservation of momentum, we would say that the mass times the velocity of the bowling ball plus the mass times the velocity of the man before they collide has to equal the mass times the velocity of the ball plus the mass times the velocity of the man after they collide. So if I put in everything I know, we'll put 5 kilograms for the man and 8 meters per second for the ball, plus 85 kilograms for the man times 0 meters per second for the man. That has to equal 5 kilograms for the ball times negative 2 meters per second, plus 85 kilograms times our mystery V. And that V is the only thing that we don't know. So let's do the algebra. 5 times 8, that's 40. 85 times 0 is 0. 5 times negative 2 is negative 10. And then we're still left with 85V. So we add 10 to the other side, we end up with 50 equals 85V, and when we plug that or when we finish off the algebra in our calculator, we get that the speed of the man is 0.588 meters per second. And that is a positive 0.588 meters per second, which makes sense. He should be moving in the positive direction if he's getting hit with a ball that was moving in the positive direction. Let's do another one. Ooh, that was a typo. A 25-gram bullet enters a 2.35-kilogram watermelon and embeds itself in the melon. The melon is immediately set into motion with a speed of 3.82 meters per second. The bullet remains lodged inside the melon. What was the entry speed of the bullet? This is a classic physics problem, and it is how they figure out the muzzle speed of guns. So it's got a little bit of practical application as well. But yet again, we're given a ton of knowns. So let's make a knowns table. We're going to start with the mass of the bullet, and it's 25 grams. Now, we always work with kilograms, so I'm going to write that as 0.025 kilograms. Mass of the watermelon is 2.35 kilograms. Looks like that watermelon starts with an initial velocity of 0 meters per second. But it does say that the melon is set into motion with a speed of 3.82 meters per second. So the V2F would be 3.82 meters per second. Now, we also are told that the bullet remains lodged inside of the melon, okay? And this piece of information tells us what that final velocity of the bullet is. It must be the exact same as the melon, since it's lodged in there. And what we want to find, so we want to find how fast that bullet was moving at the beginning. So we'll write our statement of conservation of momentum. Momentum of the bullet plus momentum of the watermelon at the beginning has to equal momentum of the bullet plus momentum of the watermelon at the end. So if we fill in 0.025 kilograms times our mysterious initial velocity of the bullet plus 2.35 kilograms times the initial velocity of the watermelon has to equal 0.025 kilograms plus 2.35 kilograms. And the reason why I'm doing that, the reason why I'm adding the mass of the bullet and the mass of the watermelon together is because those two things are both moving at the same speed. So they're moving at that 3.82 meters per second. So this makes my algebra a little bit easier if I just kind of add those two masses together and then multiply it by their same velocity. And when we finish off the algebra for this, we can find what the muzzle speed of the bullet is. It ends up being 363 meters per second.